Radiance fields model the distribution of light within a scene. Rather than defining the scene through geometric surfaces or discrete objects, they encode light as a volumetric field, generating navigable three-dimensional environments from image-based observations. In our 2023 DLA paper, we introduced radiance fields as a distinct representational category for landscape architecture, arguing that their capacity to encode atmospheric conditions more closely aligns with how landscapes are encountered than previous point or mesh-based methods. Two structurally distinct approaches are prevalent. Implicit representations such as neural radiance fields encode light as a continuous function within a neural network. Explicit representations such as 3D Gaussian splatting represent scenes through a finite set of spatial primitives, each encoding position, orientation, opacity, and color. Because explicit representations require no neural network at inference, they offer reduced hardware requirements and faster rendering. Expanding on our previous research, this paper introduces Schob, single image, high accuracy, real-time parallax, a novel model developed by Apple. The model synthesizes a 3D Gaussian radiance field from a single RGB image. View-dependent effects are encoded using a layered depth approach. Trained on synthetic and real-world scenes, the model infers absolute spatial dimensions from pixel values alone, preserving physical scale independent of image resolution or viewpoint. Within landscape architecture, this enables a meaningful engagement with body scale, eye height, and spatial relations. We employed Schob to generate radiance fields from infrared imagery captured at the National Botanical Gardens and Killiney Hill Park in Dublin. Vegetation exhibits a strong reflectance in the near-infrared spectrum, a characteristic that is captured in each radiance field, extending Schob's operational capabilities into the domains of remote sensing and technical imaging. We developed a Jupyter Notebook implementation to process images and export radiance fields in PLY format. Rather than focusing on a single site, the selection of images was designed to test Schob across varied spatial scales, landscape typologies, and light conditions, combining interior and exterior environments from close-range views to expansive landscapes. Schob's capabilities were further tested in a landscape architecture studio at UCD, where students worked with inputs such as smartphone photographs, historic images, landscape paintings, and game engine captures. The resulting reconstructions were used to navigate scenes, measure features, and explore temporal change. In a context where public geospatial data are limited, Schob provided custom site-specific spatial models accessible through standard photographic practice. These experiments substantiate a broader argument. Spatial artificial intelligence is driving a structural shift in how 3D landscape models are produced and accessed, from technically fragmented sensing and modeling processes towards situated inference-based engagements. Radiance fields, and Schob in particular, represent an early instantiation of this shift, one whose implications for design practice, research, and education in landscape architecture are only beginning to be articulated.